This is another good example of the application of the concepts that we learned in the flow measurement lecture. So as you might remember from the lecture, often we use an orifice plate or a Venturi nozzle to measure the flow rate. And how it works is we insert a plate just as shown here, and we have pressure taps, one before the plate and one after, and we measure this pressure drop and we relate it to the velocity of the fluid through the pipe, and from there we calculate the flow rate. But in this case, this is a very simple arrangement, and we are not given any pressure taps, and we want to measure the flow through this pipe which is connecting these two big tanks. So from the basic principle is of flow measurement is that we somehow need to measure the pressure drop, and we can relate it to the velocity of the flow through Bernoulli equation. So the basic principle remains the same. It's just we are not given the pressure drops, and we are given the pressure drop through some indirect measure, which is this height difference of the water levels in these two tanks. So the first thing is we want to estimate the flow rate, and we are also given this chart which gives the non-recoverable pressure loss coefficient for orifice plate. So because here we have orifice, we'll need to use this curve. So let's see how to start, how to solve this problem. Since we are given the water to be of temperature 20 degrees Celsius, I'll just write the properties of water. The density of water is 998 at 20 degrees, and the viscosity is 0.001. So these are the knowns, and we are also given this length, which is 100 meters, and which is very huge compared to the diameter of the pipe, which is just 5 centimeters. So this tells us that there are significant major losses in these pipe sections, and we can calculate those viscous losses, those major losses, from the Moody chart. So how we are going to solve this problem is we'll just assume a streamline that goes like this. So this is my point 1, because most of the information is known at point 1. Pressure at point 1 is atmospheric, so gauge pressure is 0. Velocity at point 1 is also 0, but the elevation at point 1 is 20 meters. So let's say this is my datum, this is my z equal to 0 line. So the elevation at point 1 is 20 meters. Similarly, I'll choose this to be point 2. So pressure at point 2 is again 0 because it is open to atmosphere. Velocity at point 2 is 0. Pressure at, and the elevation of point 2 by the choice of our datum is 0. So what we need to do here is just apply extended Bernoulli equation between points 1 and 2. So if you write the extended Bernoulli equation, P by rho g plus alpha v square by 2g plus z at 2 is equal to P by rho g plus alpha v square 2g plus z at 1 minus the head losses. So HL, and there is no shaft work, so the shaft head will be 0 in this case, and also P1 is 0, P1 and P2 are 0, V1 and V2 are 0. So that just means Z1 minus Z2 is basically equal to all the losses. So this is, we know this is 20 meters, and HL is basically sum of all the losses, so Ki times V square by 2G. So now remember, this velocity V is the velocity of the fluid through this pipe, and let's just see what are all the losses here. So one is the major loss due to long section of the pipe, which is 100 meters. Then we have minor losses, which are due to the entrance, the exit, and we also have a non-recoverable pressure loss due to the presence of this orifice. And for the purpose, so it is another type of a minor loss, but for the purpose of this problem, because we are also asked the pressure drop across the orifice, I will write it as a separate loss. So third is orifice loss. So if you substitute all these terms here, HL comes out to be K major times V square by 2G plus K entrance V square by 2G plus K exit V square by 2G plus K orifice. Again, beta, the geometric ratio beta here for the orifice is 3 by 5, which is 0.6 V square by 2G. And as you may know, this major loss is friction factor multiplied by the length of the pipe divided by the diameter, and so HL will be V square by 2G bracket FL by T plus. Now we can find out the K at the entrance, K at the exit, and K at the orifice from the data given. So from your formula set, K entrance is equal to 0.5 because it is a sharp edged entrance. As you can see, it is a sharp edged entrance, and similarly this exit is also sharp. So for a sharp exit, K exit is close to 1, and K orifice can be found out from this plot here. So beta is 0.6, and we are given that it is a orifice plate, so it comes out to be 1.5. So this is 1.5. So I'll just substitute these values here. 0.5 for the entrance, 1 for the exit, and 1.5 for the orifice. So so this is what calculation gives us, and the head loss is equal to Z1 minus Z2, which is 20 meters. So V square by 2G F L is 100 divided by 0.05. So the length of this section here is 100 meters, and the diameter is 5 centimeters. So that's what 100 meters, 5 centimeters is 0.05 meters, plus if you sum this, you'll get 3, and this is equal to Z1 minus Z2, which is 20 meters. So if you solve this and substitute G equal to 9.81 meters per second square, V square comes out to be 2 times 9.81 times 20, so multiplying this here divided by f times 2000. So this 2000 is, if you calculate this ratio, comes out to be 2000 plus this factor 3. So again, we are because the velocity is unknown, in the Moody chart, if you see in the Moody chart, we need to calculate the friction factor, we need to know the Reynolds number, and we'll just assume the pipe to be smooth, but we need to know the Reynolds number to calculate the friction factor here. This friction factor. So so because this is the velocity is unknown and the Reynolds number is unknown, we need to iterate by starting with an initial guess and iterate to converge to exact to an exact solution. So I'll just guess f Reynolds number to be equal to something around 5 10 power 5, and the friction factor for this from the Moody chart comes out to be equal to close to 0.02. If you go to Moody chart, so for a Reynolds number of 5 10 power 5 for a smooth pipe, the friction factor is close to 0.02. That's what I will use here. So if you do this, your estimated velocity comes out to be equal to 3.02. And now if you calculate the Reynolds number, comes out to be rho p t by mu. So if you substitute all the values, 998, 3.02, into t is 0.05, mu is 0.001. So this comes out to be 1.5 10 power 5. So the estimated RA is smaller than the guessed RE. So we need to correct for it. So is improve our guess. So we need to basically we can use this new estimated RE to be your improved guess. And now if you go to the Moody chart for 1.5, which comes somewhere here, if you go, your friction factor comes out to be somewhere close to 0.016. So your improved guess for the friction factor now is 0.016. And if you substitute it again in this formula here, I will mark this as 2. So substitute in 2, So what you will find out that V comes out to be equal to 3.33 meters per second. And now if you estimated velocity is 3.33 seconds, and your estimated RE then comes out to be rho V d by mu, which is 998 times 3.33 times the diameter. And now this comes out to be 1.6 times 10 power 5. So this is very close to our improved guess, and that gives us hope. So in the next iteration, will be more stringent. So this is good enough, but the next iteration, guess RE to be equal to 1.6 and find the friction factor. And if you do these iterations, you will converge to a more correct value of friction factor, which is 0.0162. And again, velocity won't change that much, it will be 3.33 meters per second. And your Reynolds number is close to 1.66 times 10 power 5. So this is your solution, the converged solution after performing 2 iterations. And now that you know the velocity, the flow rate is nothing but velocity times area. So it is pi by 4 times d square into v, which is pi by 4 times 0.05, because the diameter is 5 centimeters, and v is 3.33. We just calculated that. So q comes out to be equal to 0.00653 meter cubes per second. So this is the volume flow rate and answer to part A. And part B is asking us to find the pressure drop. Now finding the pressure drop is simple, because we already know the Reynolds number, we already know the geometrical ratio beta, which is small d by capital D across the orifice, which is 0.6. So from these two we can find out CD for an orifice. So part B, RED is 16630, beta is 0.6. So CD comes out to be equal to 0.609. This value comes from the chart for CD versus RED for orifice, which is given in your lecture notes, and even in exams or homework solutions you will be given this information. So now we will just use the formula for an orifice meter. The flow rate through an orifice meter is coefficient of discharge times area at throat. So here area at throat is pi by 4 times 0.03 square, because the diameter at throat is 0.03 meters, and square root 2 times the pressure drop across orifice. So I will write it as delta P orifice, and this is the unknown divided by density and 1 minus beta power 4. So now we know what Q is, we just calculated it. We know coefficient of discharge, we found it from the chart. Area at throat is known because diameter there is given. We know the density of water, we know the geometric factor. So the only unknown here is delta P orifice. So if you solve for delta P, we'll find that it comes out to be equal to 100 kilopascals. So this is the answer to part B. Yeah, so just a recap how we approach this problem. So in this problem we are given there is an orifice but there are no pressure drop taps, so we don't know the pressure drop across the orifice, and we are also asked the volumetric flow rate. So to find this pressure drop, we had to employ an indirect method because such that because the elevation of these free surfaces was given, so we used extended Bernoulli equation across these surfaces, and from that calculation we found out that the elevation difference between the surfaces is nothing but the all the losses that this flow is encountering, and these losses are major loss due to this long section, the non-recoverable pressure loss across the orifice, the minor losses at the entrance and the exit. So we found out these losses in terms of these loss coefficients, and the major loss comes out to be equal to FL by D. F is the friction factor, we get that from Moody's plot, and solving for velocity we get this expression in terms of the friction factor. Then we used an iteration method, so we guessed an RE and the friction factor, found out the estimated velocity and estimated Reynolds number, and the estimated Reynolds number was not equal to the guessed Reynolds number, so we improved our guess with this estimated Reynolds number and improved our friction factor, and from there we finally converged to these. So the velocity is this, and then flow rate is nothing but velocity multiplied by area, and this is the flow rate. And for finding out the non-recoverable head loss cross orifice, we just use this uh, equation that we found out in also in lecture notes, which relates the flow rate to the pressure drop. Yes, so that's it for this problem.